All right. Welcome back, everyone. I hope you're well caffeinated after the coffee break and ready for our last session, which is going to be focused on digital identities. And as the name suggests, digital identities are digital versions of documents like passports or driver license that allow the establishment of someone's identity or age, for example. And the development and deployment of digital identities is now being mandated by more and more regulations, including the European Union. And today, in this session, we're going to hear about some of the challenges that arise on this path that we're all on. The first talk is going to be given by Alexandros, who's a postdoc at HPI and the University of Potsdam. And he's going to tell us about some of the challenges of implementing or achieving non-transferability of digital identities, meaning that you can't just copy them from one device to another, and how to do this on legacy devices. Alexandros, stage is yours.
Thank you for the introduction. So hi, everyone. So I'm Alexandros, and I will explaining how we can make anonymous credential work on legacy phones, on the phones that you hold right now. What are the challenges and what are possible solutions? So as was mentioned, like the European Digital Identity Wallet is coming, and it's probably coming soon, and it aspires to be privacy-centric. So it has all these features that we discuss on the field, like selective disclosure, unlinkability, pseudonyms, and so on. And I have good news that, okay, these are heavily researched topics, and we know how to solve them. We know how to achieve all this. We know how to build anonymous credentials and zero-knowledge proofs. The bad news is that such primitives are more complex than, let's say, standard digital signatures or encryption schemes. And also, they have never been deployed en masse. So the asterisk there is that, okay, one can claim that zero-knowledge proofs are deployed in the blockchain space, but this is kind of an unregulated space where, things are kind of simpler. And okay, and there are some ugly facts that, well, whatever we use, it must be standardized. This is the first issue, and it's kind of rough to achieve. That is way non-trivial, and it's taking time. And also, we have some existing hardware limitations, which I will explain briefly. So, but first, let's see what is the one main barrier in deploying such constructions is that, okay, because of their nature as digital constructions, they are easily clonable. So they are basically bits. You can take them, copy them, and give it to other people. And this is very hard to prevent, especially taking into account that this can be done undetectably because, well, we want also privacy. So we can have misuse and less trust in the system. So we need to address this. And like one of the ideas to address this is to use the so-called device-bound credential. So roughly, this works by having like a device, in the real case, our mobile phone, which has a piece of hardware which is called the secure element. And inside this hardware, it leaves hidden a secret key of a signature scheme, the device secret key. And the user only knows the device public key, and it cannot access directly the secret key. But what it can do, it has Oracle access to a signing algorithm, so he can give a message and get back the signature. And the way we bound the credential to the device is that with every presentation, we also prove that we know a signature on the device public key on some random nonce given as a challenge from the credential verifier. Notational, like the green values are values that we can reveal, and the red values are values that we want to keep secret for privacy. So I follow this in all slides. Hope it helps. So okay, let's start. Let's see the basic blueprint for anonymous credentials. So very roughly, we have the issuer, the user, and the verifier, and the issuer has a signing key, the issuer's signing key, and the corresponding public key, which it shares to the user and the verifier. And when the user wants to verify herself, so first the user, of course, has to get the credential, so it sends, thank you. So the user speaks with the issuer, gives her attributes, which are basically a vector of messages. Yeah, and the issuer just uses his signing key to sign them, and now the user has this signature. So this is the credential. The message and the signature constitute the credential. And now when she wants to verify herself, so first the verifier gives some context about the presentation, and he asks to learn some of the attributes of the user. These are indexed by I. This corresponds to the so-called selective disclosure. And what the user does is basically send these attributes, the disclosed ones, and it also sends a proof that basically attests that she owns the signature that verifies with the key of the issuer, and that things are consistent. So whatever she revealed exists actually on the credential. Yeah, so in reality, we need more things than the basic blueprint. So we want extra features, such as predicate proofs, that some value is in some range, pseudonyms, non-revocation, and device binding, as I explained earlier. And the problem is that the zero-knowledge proof that the user has to send becomes too complex, and this can be problematic for various reasons. So, but before we get that, let's see how to extend the previous blueprint with device binding. So, issuing is the same. So the user takes the signature. Now, some parts of the attribute correspond to the public key of the device. So this information is encoded in the messages and is signed by the issuer. Now, when the user wants to verify herself, she gets, again, the same information, but as part of the context of the presentation, she also gets a nonce. And then she just queries the secure element and says, okay, give me this a signature on this nonce. And then the secure element gives this signature. And now the user can use these two signatures to again create the proof and guarantee that she owns both the credential, also the device that holds the secret key, and everything is consistent with what she presented. So this is how device binding can be implemented. And now the question is, okay, what signature scheme to use? And well, let's use something that is efficient, that it is post-quantum secure, and it has native super fast ZKPs and all the fanciness features. Or let's just use the ECDSA. And why is that? It's exactly because of legacy hardware. So most mobile phones that people have, they only support secure element with ECDSA over the P256 curve. And this is hard to change. So first of all, the design of secure element itself is a timely and a hard process. But more importantly, of course, we cannot ask millions of people to buy new phones that have this super new hardware and can support whatever other algorithm. So at least at the moment, we are stuck with ECDSA, and the problem with that is that this signature scheme was never designed to be proven under zero knowledge, and we get to achieve that we need to use some complex constructions, and we have some inherent efficiency costs. And okay, this is roughly what exists. So this is very rough. So basically, okay, to prove an ECDSA signature, you need hundreds of milliseconds and hundreds of kilobytes, more or less. And I call this a monolithic approach that will become evident in a bit, in contrast to what I will present. The good thing with, so note that here we use both for the issuer and the secure element ECDSA. And this has a nice thing that it is compatible with existing credentials. So we don't need to change no infrastructure. We can just use what we have, and on top of that, we just add a zero knowledge proof. The bad news is that we need complex zero knowledge proof systems and complex circuits that represent the computation, the proof of knowledge of the ECDSA. And this is particularly important for standardization, because the more complex the system, the harder it is to actually standardize them and deploy them. And also there are some inherent limitations. So basically, these zero knowledge proofs have a trade-off of prover time and proof size, which kind of lives there, and we cannot have both. So yeah, that's why in this case we see these large proofs, which can be okay, but are prohibitive, for example, for proximity presentations, where you go with the mobile and you tap it and you present yourself. So yeah. And okay, the core idea to mitigate this is to just, okay, we know we are stuck with ECDSA, but let's just use it to the minimum degree possible. To do that, the first thing is we propose this modular framework. So basically, this counters this complexity of the monolithic zero-knowledge proof I talked about earlier. So instead, we propose a kind of a divide and conquer approach, where we, instead of having this big proof, we have smaller proofs, which are conceptually easier, and in some cases, like they also allow us to do optimizations and be modular and select what we use. And we use commitments to link the various statements together. And roughly, how does this work? So the situation is exactly as before. So we have the user and the verifier, and we have the credential. I forgot here, we also have the proof of possession signature. So again, the user gets the proof of possession. Yeah, I didn't forget. Yeah, but now what changes, instead of sending this big proof, the user creates commitments on the attribute it needs to prove things about. So it creates these commitments, so the values should be equal to the ones on the credential, and the user basically now proves whatever it proved before about the selective disclosure. So it owns a valid signature, it revealed some attributes that the verifier requested, but also the commitments are consistent with the credential, meaning that whatever is committed exists on the corresponding part of the credential. And so the user makes this core proof, and it sends the commitments and the proof to the verifier, and then it can prove on top of that additional things. So, for example, it can, for the fourth commitment, it can prove that it lies in some range, and it can send this proof to the verifier. And for the eighth commitment, like let's assume this corresponds to the device public key, it can prove it knows the proof of possession, the signature of the device, which is the proof of possession of it. And okay, why is that important? Because okay, it's much simpler conceptually, and it gives the ability to choose and optimize specific parts of the component. So, for example, we can have a different signature for the issuer and the device binding. We can use different stacks for zero knowledge to make our claims. And it also allows to change things. So it gives us this crypto agility feature. And perhaps it will also be much easier to make the post-quantum transition when necessary, because we need to deploy things today, but at some point we need to change, and we don't want to redo all the work of designing and standardizing and so on. And it also allows to have more trade-offs. And standardization now becomes much easier because we can, for example, start standardizing the core proof, and then add layers on top of that for device binding and range proofs and all the fancy stuff that we want. And now, okay, like for example, an example configuration is efficient centric is, let's use the best thing we have for the issuer. Let's use BBS, for example, a pairing-based signature with native zero knowledge, and used for linking Peterson commitment, which combine very well with such signature schemes. For the secure element, as I mentioned, we don't have an option, so we must use ECDSA. And the question is, okay, how do we implement this proof of possession? And okay, what I want to argue, I want to get into details of the technique. So basically, we propose various constructions that are based on existing techniques and some new techniques to optimize efficiency. But the takeaway from this talk should be, in my opinion, that okay, we have many trade-offs to navigate, we have many options, we have many ways to implement it, and we need like to discuss what is important for each application and go for that. So the trade-offs can be on efficiency. So maybe we want bigger, smaller proofs, or we want smaller prover time. It's on system complexity itself. It's on the assumptions we use. And yeah, so these proofs are designed with modularity in mind. So they are, of course, compatible with our previous framework. And okay, the design of the proofs themselves is based on the reduction of knowledge framework from Kodapali and Parno, for those of you that are aware. But basically, this allows us to get reusable components, so parts that are common in proofs, we can reuse them, and it makes the security analysis much more elegant and easier. And okay, as I said, like the proof of possession, it's basically a signature, a proof of knowledge of a signature on what is output by the nonce, and like what we do to optimize in this recent work is essentially, so we rely on the fact that it's not a general proof of knowledge of an ECDSA signature, so the nonce is public, we take advantage of that, and we take advantage also of the fact that we can reveal part of the signature, so at least in a model that assumes a trusted secure element that does not try to de-anonymize the user. And so Carla Friedrichs will give a relevant talk discussing about alternative models in Tuesday, I think. And yes, so basically, like we managed to reduce the problem of proof of knowledge of ECDSA to essentially mostly a scalar multiplication over P256. And basically the challenge on that is that we have now, okay, the public key must be committed, must be hidden, because otherwise we lose privacy. And so it's one of the commitments presented during the presentation. And the problem is that BBS work on pairing groups, so for example, BLS12 curve, while the ECDSA, it works on P256 because this is what the current device supports. So somehow we need to argue, we need to prove things about the commitment key, both in both curves. And there are many ways to do it that give different trade-offs. Yeah, so the first approach that we propose is basically using generic zero-knowledge techniques and optimized techniques for foreign field arithmetic, so basically emulating P256 arithmetic in BLS12. And this is the nice feature is that it's succinct and it only relies on the BLS12 curve and basically the assumptions underlying the Plonk proofing system. The bad thing is that, okay, it uses kind of a heavy toolkit from the SNARK work, but probably this is not necessary. So yeah, basically we took a machine gun, like a proving system that is very general to prove something very simple. So probably like we can like stripe off parts of the SNARK and get something much more less complex in the sense of the tools that are used. The second construction is again SNARK based, but this time it's based on bullet proofs for those of you who are aware. So this is the most succinct constructions we propose, and it has quite fast proving. The trade-offs regarding the assumption is that we now need to rely on a non-standard curve. So basically, because we don't do foreign field arithmetic, we need to introduce a new curve, and basically what we need is the discrete logarithm to hold on this curve. This is the Tom curve introduced by ZK-test and the CDLS. And yeah, the proving system is fairly simple, so it doesn't have all this machinery, so it's quite easy to understand and to see what is happening. So it's somewhat a middle ground. And the third construction, it was initially proposed by UBIC. It was implemented by UBIC, and it's purely based on Sigma protocols, which makes it conceptually the simplest construction. It relies again on the same curve, and the trade-off is that now we lose succinctness, and we need to have larger proofs. But as you can see, there is a wide range of spectrum, and of course it's non-exhaustive. One can try, for example, to optimize the proving time and see what trade-offs arise in this case. And yeah, so I added some numbers. So just to clarify, these are only the proof of possession parts, the three constructions I presented. So they don't consider the presentation, but like this is basically the overhead for any reasonable presentation. And as you can see, like we get decent proving times. Actually, the two native constructions have quite small proving time. And the proofs range, like on the succinct ones, 4 kilobyte, 1.5 kilobyte for bullet proofs, and you get the bigger proofs in the Sigma one. So if you're interested, I have a demo on the Sigma one, so reach out and I can show you how you can do a presentation on the mobile. Unfortunately, I don't have for the others. And yeah, like this is actually a proof based on the second construction with the most succinct one, which I just put it to demonstrate that the proofs are small enough that you can actually prove them in QR codes, and you already have more capacity for the other parts of the presentations themselves. Okay, and some concluding remarks, like we aim to build a complex system, so the way to do it is to go modular as possible, so we get more trade-offs, we get more optimization, more flexibility. And for the device binding, okay, yeah, we are stuck with ECDSA for now, but it's more than feasible actually to prove it, and we can actually choose what we want to prioritize. And just a word of caution, so, okay, the system, it will have a deep societal impact, and this talk was from the technical lens, from the cryptographer's lens, of how we do things, but I think it's important to have discussions on what this will mean for our lives and society, and I'm looking forward to the next talk, which would go deeper into that. And finally, so yeah, in our team, like we do our best to bring this to life with the best possible terms. So we contribute to research, we contribute to standardization, and yeah, I want to thank my colleagues for the common works, and that's it. These are the two papers I mentioned, so yeah, feel free to read them. And
Thank you, Alexandros. We will take one quick question.
Did you consider using field-agnostic proof systems for P256?
Can you give an example? Like, what do you mean field-agnostic?
I guess the limitation, I'm assuming you had to use a different field so that you could have two-adicity, so you could apply a proof system. I can't remember which one it was in the benchmarks, but you could also do it in a field-agnostic proof system. We can talk about this later.
Yeah, I'm not sure what this is, so yeah, happy to. Okay.
Hi, thank you for the talk. I was wondering, these secure elements that only do ECDSA, P256, how rich is the API? Would you be able to use them as generic integer multipliers?
It's a bit unclear, honestly, for the API. So as far as I understand, like now they just support giving out signatures. So there is a feature that it's the pre-hashed, I think, where you can just give the hash of the message and get the signature. But as far as I can tell, this will be, it's deprecated and it will not be used. So it's in general limited and yeah, kind of hard to change.
Thank you.
Let's thank Alexandros again.